Here's a sentence for you. This statement is false. Read it again. If it's true, then it's actually false, exactly like it says. But if it's false, then it's telling the truth, which means it's true. There's no way out. Not because you're missing something, because there genuinely isn't an answer. Most things we call paradoxes aren't actually like that. They feel broken, but they're not. We just haven't looked closely enough yet. There's a whole category of famous paradoxes that are actually true once you understand them. There's another category that feel true but are secretly hiding a mistake. And then there's a small, strange third category, the real ones. The ones that stay broken no matter how carefully you check. By the end of this video, you'll know exactly which is which, and why almost nothing you've heard called a paradox actually deserves the name. Start with the first category. A veridical paradox is something that sounds completely absurd, and turns out to be completely true. Here's a classic one. You're on a game show facing 3 doors. Behind one is a car. Behind the other 2, nothing. You pick a door. The host, who knows what's behind each one, opens a different door, revealing nothing behind it. Then he asks, do you want to switch to the remaining door or stay with your original pick? Most people's instinct is that it doesn't matter. It feels 50-50. It's not. Switching actually doubles your odds of winning. This is called the Monty Hall Problem, and it's been formally proven, tested, and simulated millions of times. It still feels wrong to almost everyone who hears it for the first time. That feeling is the whole point. The paradox isn't in the math. It's in your intuition failing to keep up with it. Here's another. Take a room with just 23 people in it. What are the odds 2 of them share a birthday? Most people guess something low, maybe 10 or 15%. The real answer is just over 50%. With only 23 people, in a year with 365 possible birthdays, it's more likely than not that 2 match. It sounds impossible, it's simply true. The second category runs the opposite direction. A falsidical paradox feels true, sounds airtight, and is actually false, because a mistake is hiding somewhere inside the reasoning. The most famous example is over 2,000 years old. Achilles, a legendary runner, races a tortoise. Because he's so much faster, he gives the tortoise a head start. The race begins. By the time Achilles reaches the tortoise's starting point, the tortoise has moved slightly further ahead. By the time Achilles closes that new gap, the tortoise has moved again. This repeats forever, an infinite number of gaps to close, which seems to mean Achilles can never actually catch the tortoise. Except obviously in the real world, faster runners catch slower ones constantly. The mistake isn't in the logic of the gaps. It's in assuming infinite steps must take infinite time. They don't. An infinite series of shrinking gaps can still add up to a small, finite distance covered in a small, finite amount of time. The paradox isn't a flaw in reality. It's a flaw in the argument. Mathematics has its own version of this trick. There are famous, deliberately broken proofs that claim to show 2 equals 1, walking through what looks like valid algebra, step by step until you reach an impossible conclusion. Every single one of these hides the same error somewhere in the middle, almost always a hidden division by 0, disguised well enough to slip past you if you're not looking for it. Which brings us to the third category, the real ones. An antinomy isn't hiding a mistake, and it isn't secretly true underneath the confusion. It's a genuine contradiction, built from 2 lines of reasoning that both seem completely sound, and simply can't both be right. You already heard one at the very start of this video. This statement is false. Logicians call it the liar paradox, and it's not a trick sentence with a clever answer waiting to be found. Philosophers have wrestled with it for over 2,000 years, and it still doesn't resolve cleanly. Here's a version that actually broke mathematics for a while. Imagine the set of all sets that do not contain themselves. Does that set contain itself? If it does, then by its own definition, it shouldn't. If it doesn't, then by its own definition, it should. This is Russell's paradox, and it wasn't just a curiosity. It exposed a genuine flaw at the foundation of set theory, the branch of math that everything else is built on, forcing mathematicians to rebuild the foundations of their own field from scratch. And here's one you don't need to be a mathematician to feel. A ship sails for years. One by one, every single plank is replaced, until eventually not one original piece remains. Is it still the same ship? Say yes, and you have to explain what sameness even means if nothing physical survived. Say no, and you have to explain exactly which plank, replaced on which day, is the moment it stopped being itself. There's no clean answer, just 2 reasonable positions in permanent, quiet conflict. So here's the idea worth carrying with you. Most paradoxes aren't broken. They're solved. We just hadn't caught up to the solution yet. Only a small handful stay broken, no matter how closely anyone looks, and those are the ones that actually deserve the name. So the next time you hear something called a paradox, ask which kind it actually is. If it's veridical, it's just waiting for your intuition to catch up. If it's falsidical, there's a mistake hiding somewhere, and finding it is the whole game. And if it's a real antinomy, you're standing at the edge of something genuinely unresolved. One of the very few places where human reasoning simply runs out of road. Those places are rare. And they might be the most interesting places thinking can actually take you. Next time, we'll explore a related question. Not what happens when logic breaks, but what happens when your own mind runs experiments it can never actually perform. Every thought experiment explained.